Hi there. Today we're going to start our first lesson in geometry. Our goal, by the end of the lesson, we should be able to name objects that look like points, lines, and planes and describe what those things are in geometry. We're going to begin with the simplest geometric form, and that is a point, which most of us would agree we draw just a little dot, right? In geometry, that's not really a point, because points are imaginary. In fact, a point is really a location in space that has no shape or size, right? We picture it with a point because that's what we're familiar with. However, it doesn't really exist there. The way that we name points is with a single capital letter. This could be called point A. A single capital letter names a point. The next of our geometric species today, entities, is the line. And you can see we have two lines pictured here. The way to name a line is by either using 2 points that lie on this line, and I'm going to call those B and C. That is, we could name that line the line BC. Symbol has an arrowhead on both ends. You also can name a line with a single lowercase letter, and I'm going to use L because that just kind of makes sense. There are the naming conventions. As far as describing a line, many people will say that a line is the collection of points that extends infinitely in 2 directions. Okay? I like that. One thing that I want to make sure we know by the end of the lesson today is that lines cannot bend. Okay? If we're extending in opposite directions infinitely, it means we go on and on forever in the same direction, no turning. A plane, by that same token, some people will call a collection of lines, okay, that extends infinitely in 2 dimensions. Okay? Not directions, but dimensions. And I kind of like that description. Most of us would say in layman's terms a flat surface. Okay? A plane, folks, is named by a single uppercase cursive letter. That is, I could call this plane R, like that, or by 3 points that don't all lie on the same line. That's what it's called collinear. 3 points that are not collinear. D, E, and F. So we could call this plane DEF. Oftentimes planes are named by more than 3 letters, especially if we're talking about surfaces on the sides of a cube, say. We've got a little way for you to test your knowledge here. I want you to pause the video for a few moments and answer these questions. This plane cannot be called plane CAB because point A is not on the plane. Okay? Plane R is okay, single capital cursive letter. Plane DEC is okay, D, E, and C. 3 points, not all on the same line. That's all right. The line containing points E and D could be called line ED. It can't be called line F. F is a point here. And the capital S, no. Lines, if you're going to call them by a single letter, it's lowercase. So A is the correct choice here. The lines S, Q, and R are coplanar. That term means lie in the same plane. And I believe that that is not true. S and Q are in the same plane, but R goes through, as you can see. That is false. Points F, E, and D are collinear. That means lie on the same line. And as you look at our picture, F, E, and D do lie on the same line. That is true. I'd like to take just a moment and talk with you about 3 related geometric entities. I call them things in geometry. Since we have this picture here, this is a good time to talk about it. A line segment is a piece of a line that's bounded by 2 points called the segment's endpoints. If we wanted to talk, for example, about the segment CB, we would refer to it this way: CB with a segment on top of it. A ray, folks, is also a piece of a line, but this time It's the piece of a line or a piece of a line bounded by only one endpoint. You use two letters when you're talking about a ray. The first one is the endpoint. So I'm going to talk about the ray FB here. Starts at F, goes in the B direction. When I'm naming that in writing, I put that endpoint first, F. B just tells me the direction that that ray is pointing. Okay? A pair of opposite rays are two rays that share the same endpoint and together will form a straight line since they go in opposite directions. In keeping with what we just looked at, ray FB and ray FC, starting at F but now going the opposite direction. FB, FC, a pair of opposite rays. Again, I just want to remind you that first letter is the endpoint. The second shows direction. I'd like you to take just a couple of minutes and think about a couple of objects that might look like what you consider to be a point, a line, or a plane. I'm going to do that. I'll ask you to pause the video and let's compare in just a couple seconds. Alright, I have my ideas here. I said the lock on my doorknob looks like a point, or what I would picture a point to be, or the tip of my pen or pencil. Okay, not the entire thing, just the tip. A line, well, a line has to have two dimensions, go in two dimensions, and a windowsill is a good model of a line, as is a pencil. The only thing is, you got to remember that in geometry, lines extend forever. A plane might be modeled by the top of my desk or the floor or ceiling in my house or the room that I'm in now. Okay? I'd like us to take just a second and get a chance to draw some geometric entities. Let's look at this description and see what it wants us to do. We're to draw a line in the coordinate plane that contains 2 points, x and y, whose coordinates are given, and some point w that is not collinear with x and y. Well, that doesn't seem to be too difficult. Over 3, down 1, there's the x point. Back 3, down 4, there's the y point. So there's my line xy. And I need now some point w that's not collinear. That looks like a fine place for w. The next of these instructions asks us to draw a plane Q. When we are picturing planes with pencil and paper, we use parallelograms for the plane. Even though we know that planes extend infinitely, they don't have edges like this. This is the way we show them if we're drawing. We want our plane to contain 2 lines, a line R and a line S. And those lines are supposed to intersect at some point P. So, there we go. An R and an S, those are the line names. Point P, capital P. Very good. We want to take just a few seconds and talk about 3D drawings, which show three-dimensional objects drawn in space. That's just the name for three-dimensional stuff. It exists in space. Planes are represented by parallelograms, often rectangles, and lines and segments that are hidden from your view are represented with dashes. So as you look at the box here, how many planes are we showing? Well, we've got a top, a bottom. This is a rectangular prism. A top, a bottom, and 4 sides. That's 6 planes. 3 collinear points. 3 points all on the same line. I believe there's only one place in this picture that shows that. Oh, no, there were 2. BKC, though, is the one that's listed. The other would have been AJB, and that's not a choice. Are the points A, D, C, and G coplanar? Well, let's locate them. A, D, C, and G. I don't think so, you guys. A, D, and C are all in the top of this box. G is in the bottom. That means that they are not existing in the same plane. In order for a plane to contain A, D, C, and G, that plane would have to bend, and they cannot do that. We're going to take just a few minutes and talk about where all of the study of geometry came from, and that is a Greek named Euclid, okay, a long time ago. He set forth a series of 9 postulates. We're going to talk about 4 of them today that represent the foundations of geometry. A postulate, folks, is a statement that is accepted as fact, even though it cannot be proven, is accepted as fact. And Euclid's first postulate concerns 2 points. And what he had to say about that is, between any 2 points or through any 2 points, there exists exactly one line. That is, since lines don't bend, if I want to catch both A and B, there's only one line that will do it, and I've pictured it right there. Now I'm asking you to apply Euclid's postulate here and graph the line that passes through these 2 points, where A is -4 and 1, back 4, up 1. B is over 2 and up 3. There you have it, the line AB. In fact, that's how we would look at that thing, or that's how we would name it. His second postulate involved 2 lines which intersect. And since lines cannot bend, that's by definition, if 2 lines are going to intersect, then the place where they do intersect, their intersection, is exactly 1 point. Neither of these lines can come back and bend and cross someplace else. If they're going to cross, they cross in 1 point. Now, I wanted to bring this home to you in a way that you would recognize, so I want you to think about your algebra class last year. You learned about solving systems of equations, and the system's solution is the point where those 2 lines cross. The lines I've graphed here are y equals x minus 1. That's this line whose intercept is at -1. And y equals -x plus 5, which has a negative slope, are going down and crosses at 5. The intersection to that system is the point that is over 3 and up 2. Okay? All right. The third postulate. What happens when 2 planes intersect? A good way to answer this question is to look at 2 of the walls in the room that you're in. 2 planes, if they are going to intersect, must intersect in a single line. If you think about that, looking in the corner of the room, you'll see the line up and down between 2 walls. They share that line. That's their intersection. As you look at the drawing that we have here, plane OIL is this one, plane ILC is this one. The only thing those planes have in common is the line IL. This next activity asks you to find and darken the intersection of 2 planes, mat and rom. Well, folks, mat is the top of this box. Rom, R-O-M, is the side of this box, and the only thing that's in both the top and the side is the line MA. When 2 planes intersect, their intersection is a line. The last of Euclid's postulates concern 3 points not all on the same line, and what he says about that is, a plane is defined by 3 points not all on the same line. 3 non-collinear points form exactly 1 plane. Keeping that in mind, we'd like to ask you to answer some questions about this 3-dimensional rectangular prism that's shown. First off, we want to find and shade the plane that's formed by points E, C, and L. E, C, and L right here. All 3 of those exist on the top of this box. The next activity asks us to find and shade the plane that's formed by points U, D, and M. Here's U and here's D. M is way over here. And folks, the plane that contains those points would also contain this point. And it crosses through the middle of that rectangular prism. I wouldn't say that that was a plane that's shown. However, it is formed by those 4 points. The next question, how many planes contain the points D, I, and G? Here's D, here's I, here's G. Those points are not all on the same line. According to Euclid's postulate, only 1 plane contains them. The last of our questions, how many planes contain the points G, O, and M? G, O, and M. Those all lie on the same line, and you can see right in this box that at least 2 planes contain them. I would submit to you that if you consider rotating this end about that line, that there are many, many, many planes that contain G, O, and M. Since they are collinear, infinitely many planes contain those 3 points. Again, that's because they lie on the same line or are collinear. All right, the next thing for you is to get out to the website, try the U-Try exercise for its lesson 1-2, and we'll talk about this in the morning.